Welcome to Mr. Tompkins EdTech and my series of exam question compilation videos on key topics you might still be struggling with. This particular video covers the speed-time graphs. I've taken related questions from my past paper walkthroughs and given them to you here back to back. These compilation videos will give you a deep dive on topics you are still finding challenging, giving you more of an overview, helping you recognise command words, identify key features and strategies, building your confidence and helping you apply these techniques for future papers. If you find it helpful, please give the video a thumbs up, it will really help me out. Also, if you haven't already subscribed to my channel, why not do that now? I'll be making lots of these compilations over the next couple of weeks and you'll get notified of these as soon as I upload them. Right, let's get into it. Question 8. The graph shows the speed of a tram as it travels from the library to the town hall. And we've got a little diagram underneath. It's a speed time graph, isn't it? So we've got speed in meters per second up the side, and I assume that's time along the bottom in seconds. Calculate the deceleration of the tram as it approaches the town hall. Okay, well, I assume that this upward part of the journey, that's it going from the library to the town hall. So you can see it's accelerating for all that period, and then it kind of reaches a peak speed, and then for the second part of the journey it's decelerating at a constant rate until it reaches a stop here. Okay, so calculate the deceleration part of the journey. Now on a speed time graph, acceleration is equal to the gradient of the line, isn't it? Now gradient is change in y divided by change in x, isn't it? In this case it's the change in the speed divided by the change in the time. So the speed changes from 6 down to 0 then, isn't it? So that's a change of -6 actually, because it's decreased. And the change in y is this distance from here to here, 85 subtract 65. Okay, which has got a difference of 20. So the acceleration is -6 over 20, which is -3 over 10, which is -0.3, equals -0.3. So if the acceleration is -0.3, then the deceleration is just 0.3, isn't it? Okay, because deceleration is how quickly it's slowing down, whereas acceleration is how quickly it's speeding up. So a negative acceleration means a positive deceleration. Right, part B. Calculate the distance travelled by the tram between the library and the town hall. Now distance travelled is area under the speed time graph. Okay, and this case we've got two distinct areas, haven't we? We've got this one here, which is a triangle, and we've got a separate triangle here. Okay, so we've got two triangles. Another way of looking at it is those two triangles make one big triangle, don't they? So you can use the baseline all the way across from there to there, which is 85, and the height of the triangle is 6. So I'm just going to work it out as one big triangle, half baseline of 85 and a height of 6. So half 6 is 3 lots of 85, 240, 255, 255, and what's the units? It's in meters of second and seconds, so that's going to have to be meters then, isn't it? 255 meters. Part C says, what was the maximum speed of the tram as it travelled between the library and the town hall? Give your answers in kilometers per hour. Okay, so let's have another look at the graph. You can see from the graph its maximum speed is going to be that tip point on the graph, the highest point on the graph, isn't it? And we're already told what that is. That's 6 meters per second. So this question is just really about conversion, isn't it? We need to convert that 6 meters per second into kilometers per hour. Okay, so maximum speed is equal to 6 meters per second. So now we need to convert meters per second into kilometers per hour. Okay, now there are 1,000 meters in a kilometer. There are 60 seconds in 1 minute, and we've got 60 minutes in 1 hour, haven't we? So if we're going to convert this from meters per second into kilometers per hour, we're going to have to take that 6, divide it by 1,000 to go from meters into kilometers. We're also going to have to multiply it by 60 to go from seconds to minutes, and then multiply it by another 60 to go from minutes into hours. So what's that? Reaching for the trusty calculator. 6 times 60 times 60 divided by 1,000. That comes out to be 21.6. 21.6 kilometers per hour. Does that sound reasonable? Yep, it's not super fast, is it? It's probably what you'd expect a bus to be traveling at. Question 12. An athlete goes for a training run. The graph shows their speed as they run. So this is a speed time graph. So we've got speed in meters per second along the top, and time in seconds along the bottom. Write down the athlete's acceleration between 400 seconds and 1,000 seconds. Okay, so between 400 seconds and 1,000 seconds, we're talking here. So what's the acceleration here? Well, acceleration is equivalent to the gradient of a speed time graph. And between 400 and 1,000, the line is flat, so the gradient is 0, and therefore there's no acceleration. So between 400 and 1,000 seconds, the answer is 0. There's no acceleration. Okay, and it says work out the athlete's average speed in meters per second during the 1,200 seconds. You must show your working. So drawing my distance, speed, time triangle, DST. What do I know? What do I need to find? Okay, well, I want to find average speed, don't I? It's this one here. This is the one I want to find. That's the one I don't know. Okay, now I know time. Time is easy squeezy. That's just the amount of time for the whole journey. That's 1,200 seconds, isn't it? Okay, what about distance? Do I know distance? There isn't distance anywhere in the question, but I do know that the distance travelled is equivalent to the area under a speed time graph. Okay, so if I can work out all this area here, then that is going to be the area under the graph. Okay, so what is the area under the graph then? So in here, look, what is all this area? This is the distance. Okay, now the shape of it is a trapezium, isn't it? And I could break it down into a rectangle and 2 triangles and work them out separately and add them up, but you know, I'm a mathematician. I can use the formula for a trapezium if I want. Okay, so then half a plus b times h then, isn't it? Okay, so a and b are 2 parallel sides, so that's going to be this length and this length, isn't it? Okay, they're my a's and b's, and then h is going to be the distance between them that way. Okay, so what's a? A is the difference between 400 and 1,000, isn't it? So that's going to be a half of a, which is 1,000, take away 400, that's 600, plus b, which is 1,200, times h. H is from 0 to 4, that's 4 then, isn't it? Times 4, okay? So, I'm going to just divide that 2 into the 4, get rid of it straight away. And that leaves me with 600 plus 1,200, that's 1,800, times 2, that's 3,600. So that's 3,600 meters, I guess. Okay, so then that's my distance then that I can include down here in this calculation. So that's 3,600 then, okay? So, using the DSD triangle, covering up the thing I want to find, that tells me that average speed is going to be distance over time, which in this case then is 3,600 divided by 1,200, Cancel, 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 cancel. 36 divided by 12. That is 3 somethings. 3 what? Meters per second? 3 meters per second. Question 13. The graph shows information about the speed of a vehicle during the final 50 seconds of a journey. At the start of the 50 seconds, the speed is k meters per second. The distance travelled during the 50 seconds is at 1.35 kilometers. Work out the average speed of the vehicle during the 50 seconds. Give your answer in meters per second. Well, average speed is just distance travelled, total distance travelled, divided by total time taken. So we can see from both the graph and also from the question that the time taken was 50 seconds. So that's going to be my divisor, 50. So we know that the distance is 1.35 kilometers. There's 1,000 meters in every kilometer. So 1.35 kilometers is going to be 1,350. Okay, so I've got 1,350 divided by 50. So I'm just going to cancel those zeros out. 135 divided by 5. Divided by 5 is the same as doubling it and dividing by 10. So 135 times 2 is 270. And then divided by 10 is 27, isn't it? So it's going to be 27 meters per second. And the second part of the question, we need to find out what the value of k is, which is this speed up here, isn't it? This is k. So we need to find that value there. Okay, how might we do that? Okay, well, we know that the total distance travelled is 1.35 kilometers, or 1,350 meters. And distance travelled in a velocity time or a speed time graph is the area under the curve. So this space in here is going to be 1,350 meters altogether. That space under the curve. Now this space under the curve you can divide up into 2 distinct areas. You've got like a rectangle part and a triangle part. Oops. Put a line in there. So area of a triangle, area of a rectangle. So the area of the triangle is half base times height, isn't it? So this bit in here is going to be 1/2 of the base. 40 to 50 has got a base of 10 times the height, which is k. In other words, it's 5k. And the rectangular part is just base times height, or length times width. So the base there is 40 and the height is k, so this is going to be 40k. Okay, so altogether then our total area is going to be my 40k plus my 5k, and that is equal to 1,350 meters. Okay, so 40k plus 5k, that's 45k. Okay, so then to find k, I'm just going to divide both sides then by 45, and that should tell me what k is. Divide by 45, divide by 45. 45's into 1,350. That's not so nice, is it? But 45 is half of 90. If I could just double top and bottom, make that 90. Make the top one 2 lots of 1,350. That's 2,700, isn't it? I can cancel that with that, and then I've got 270 divided by 9 then. 9's into 270. 9's into 27 go 3 times. So k then is going to be 30. Okay. Part C, calculate the gradient of the graph in the final 10 seconds of the journey. So we've got that triangle. So the height of this triangle was the value of k, wasn't it? It was 30, and the time taken along the bottom was 10. So then the gradient of this line is going to be change in y, which is 30, divided by change in x, which is 10. Well, it's actually going to be minus 30, isn't it? Because it's sloping down. So it's going to be negative 30 over 10, which is minus 3. So the gradient is negative 3. Part 2 says describe what the gradient represents. Okay, well, the gradient of a speed-time graph is the rate of change of speed with respect to time. And the word we use for the rate of change of speed is acceleration. not ACE. Acceleration. So 2 marks though. Can't just be 2 marks for one word, surely. Well, what else might they want us to state? Well, we know it's acceleration. What about the units? What is the unit? So it's acceleration in meters per second, or ms to the -2. So it represents acceleration in meters per second. Question 14. The graph shows the speed of a train during the first 60 seconds of motion. What is the speed of the train after 9 seconds? Well, if we find 9 seconds on our scale and read up, we should then be able to read across and find the speed at that time, which is that 12? Looks to be like 12 to me. So it's going 12 meters per second at that point. Okay. What does the straight line suggest about the speed of the train over the first 15 seconds? Okay, so the first 15 seconds is this section of the graph here, isn't it? The graph is a straight increasing line. So we could say either that the train is accelerating at a uniform rate or the speed is increasing at a uniform rate. Either is acceptable. So I'm going to say the train is accelerating at a uniform rate. Okay, and then we need to work out the average speed of the train in meters per second during the 60 seconds. Right, well, average speed is total distance travelled divided by total time taken, isn't it? So av speed equals distance travelled divided by time taken. Well, time taken is no problem. We know it's 60 seconds. So I'm going to be dividing by 60. What distance was covered though? Now you probably know that the distance travelled is going to be the area under the distance time graph. So you can think of it as 2 triangles and a rectangle. So the area of the rectangle in the middle is 15 to 50. What's that? So that's 35 times 20. So this is 35 times 20, which is 700 meters. This one is going to be half of 10 times 20. Half of 10 times 20. That's going to be 200 divided by 2 is 100. And this one is going to be half of 15 times 20, which is 150. Okay, so then the total distance travelled then is going to be 700, 150 and 100. So that's 950. 950 divided by 60 comes out to be 15.83 reoccurring. So I'm just going to round it off to 15.8. And that's going to be in meters per second. Question 18. Here is a velocity time graph of a car, and we're asked to estimate the distance travelled in the first 10 seconds. Okay, so distance travelled is the area under a velocity time graph, so we need to estimate the area under the graph between 0 and 10. So we want the area under the graph to the left of this line. So we want this area in here. Now you can see that it's got a curved edge, which is not very helpful, but we can estimate the area by creating an approximate area that is similar to our original area. So if we put a straight line between there and there, we can estimate the area to be the area of that triangle. And obviously it's going to be slightly less than our true area, but it should be reasonably accurate. So area is approximately equal to that triangle, half base height, which is going to be half the baseline, which is 10, times the height of the graph at that point there. Was that 45? So 45 times 10 is 450, divided by 2 is 225. So I'm going to estimate it to be 225 meters. Question 19a, the graph shows the speed of a vehicle during the first 40 seconds of motion. Calculate the distance travelled by the vehicle during the first 40 seconds. Okay, now my graph went a bit weird when I printed it out, so I've just kind of quickly drawn on the numbers a little bit more clearly. Now let's have a think about the motion of this car. It's starting from 0, it's speeding up to 30. That's a period of acceleration, and then it's carrying on at the same speed for a number of seconds after that. So it's accelerating for the first 15 seconds, and then for the rest of the up to 40 seconds it's carrying on at a uniform speed. Now we want the distance traveled. Now the distance traveled is going to be the area under the graph. Okay, it's just a fact. Area under a speed time graph gives you the distance traveled. Okay, so what we need to do is work out what the area is under that diagram. Now it's got those two sections, isn't it, where it's accelerating and then is uniform for a bit. So I'm actually going to divide the graph up into two parts, and I'm going to calculate the areas separately. I could just do it as a trapezium, but I'm just going to divide it up and do it as a triangle and a rectangle. Okay, so either is acceptable. You could just use the trapezium area formula, but I'm just going to use the triangle and the rectangle because it's a little bit easier. So the area is going to be the combination of those two areas, and isn't it? It's going to be like half base height for the triangular part plus the length times width for the second part there, isn't it? So half base times height. Now this triangle part has got, what is the base? The base is 15, and the height, this distance down here, what's that? That is going to be 30 then. So it's got a base of 15 and a height of 30. So that's a half times 15 times 30 plus length times width of the second of the rectangular part. So that's the length, isn't it? 15 up to 40. So that's got a length of 40, take away 15, that's going to be 25. So the length is 25. What is the height? It's going to be the same as the last one. It's going to be 30. Okay, so it's 25 times 30, isn't it? 25 times 30. So half of 15 times 30, or 15 squared, what's that then? That's 225 plus 25 times 30, 750 added together. 750 then added together, that is 975. What's the units? We've got meters per second and seconds, so that's going to give me meters then. It's 975 meters. Question 21. We've got a speed time graph which we're told represents the speed of a skier, and we're told that Nick wants to estimate the distance travelled by the skier in 140 seconds. Now distance travelled is the area under the graph, so we're going to have to work out what this area is. So he works out the area of the triangle with vertices 0, 0 and 140, 0. So 0, 0 is here, and 140, 0 is here, and the other vertex is at 99.8. 99.8. So the tallest point on there. So he's going to estimate this as a triangle like this. Triangles are easy to work out the areas for, whereas wibbly wobbly lines, not so much. Rulers give me jip. Okay. So, going to work out the area of that triangle rather than the wibbly wobbly area. Does Nick's method give a good estimate? Tick the box. I would say it does on the whole. You've got this bit here which is an overestimate, but it kind of matches up with this bit up here, which is an underestimate. Those two areas are fairly similar. You've also got this little bit up here which is an overestimate, and quite a large area down here which is an underestimate. So if you do use this approximation, then I would say that the answer you're going to get is a slight overstatement of the distance travelled, because, as I say, this bit down here is bigger than this bit, so your area is going to be bigger than the area under the graph. However, so I'm going to say that overall that yes, I think it is a good estimate, and the reason for that is the areas above and below the lines of the triangle are roughly the same size. And I think that, along with the work I've done on the diagram, is going to be sufficient evidence for the 2 marks. Okay, so part B, use Nick's method to work out an estimate of the distance. Okay, so basically we just need to work out the area of that triangle then. So area of a triangle is half base times height. So the baseline is of length 140, it's from 0 to 140, and the height is 9.8. That's the height there, 9.8. So it's going to be half times 140 times 9.8. Which I get as 686 meters. Okay, Helen uses a different method. She starts by estimating how many of the smallest squares are in the region between the graph and the horizontal axis. Her estimate is 1,550 squares. Complete Helen's method to estimate the distance. So it looks like Helen had a lot of time on her hands then, and she's counted all these little squares that lie underneath the graph and added them all up, and she's found there's 1,550 of those. So in order to then take that and turn it into a distance, we need to know how much one of those squares is worth. So one of these squares has a, so it's a square, but this direction on the scale is going to be 2 units, representing 2 seconds, and this unit on the scale is 0.2 of a meter per second. So in order to turn her 1,550 squares into an area, we need to work out the area of this, well, it's a rectangle actually, work out this rectangle and times it by 1,550. So area is going to be a 1,550 teeny tiny squares times 2 times 0.2. 620. Bit of a bonkers method, but there you go. Question 21. Here is a speed-time graph showing the speed in meters per second of an object t seconds after it started to move from rest. So we've got time along the bottom going from 0 up to 5, and we've got speed in meters per second, topping out at 8 meters per second. Using 3 trapeziums of equal width, find an estimate for the area under the graph between t is equal to 1 and t is equal to 4. Okay, so we need to find the area between here and here, don't we? Okay, and we need to break it into 3 trapeziums. So I'm guessing we do it here, 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 and here. Now there is actually something called the trapezium rule that you learnt at A level, which is pretty much this technique, but I'm assuming you don't know the trapezium rule formula because you're in year 11, you're a GCSE student. So what we're going to do is just going to find the area of the 3 trapeziums, and we're going to add them together, old school style. Okay, so in order to work it out, we're going to have to know this height, this height, this height, and this height, so that we can work out the sides of the various trapezium. So that one's easy enough to read. That one's a 4, isn't it? So that side is a height 4. This one is a height 6. This one, what's that? 7 and a bit. 7.2. 7.2. And then this one is 7.8. Okay. So we've got 3 trapezium. The area of a trapezium is a half a plus b h, isn't it? Okay, the 2 parallel sides added together, halved, and then multiplied by the distance between them. Okay, now for each of these, h is 1, isn't it? 1, 1, 1, 1. That's h because they're lying on their sides. So each one of these has a height of 1. So we know h for all of these is the same. H, H, and H, they're all the same. So we're just going to find 3 areas. I'm going to do area 1. Let's do area 1, area 2, area 3, and then we're going to add those areas together. So for area 1, I've got half a plus b, where a is 4 and b is 6, times h, which is 1. What's that then? 4 plus 6 is 10, times 1 is 10, divided by 2 is 5. So that's 5. A2 is half of 6 plus 7.2 times 1. What's that? 6 plus 7.2 divided by 2. That's 13.2 divided by 2. 6.6. 6.6. And then I've got A3, which is a half of 7.2 plus 7.8 times by 1, which is, well, 7.2 and 7.8 is 15. 15 divided by 2, that is 7.5. Okay, so the area under the curve then is going to be equal to A1 plus A2 plus A3, which is 5 plus 6.6 plus 7.5. I'll just move that down a little bit. Which comes to, what does that come to? Feeling lazy. Type it into the calculator. 5 plus 6.6 plus 7.5. That comes to 19.1. Okay. Now, what does this area represent? Well, the area under a speed time graph is distance, isn't it? So it represents distance travelled. So presumably that 19.1, because I had speed in meters per second and time in seconds, so I'm assuming then that's 19.1 meters that the object travelled then during the course of the time between 1 and 4 seconds. Okay. Question 28. A horse runs in a field. The speed time graph represents the first 12 seconds of the run. After how many seconds has the horse run a distance of 75 meters? Okay. So this is a velocity time or a speed time graph. Now the distance traveled in a velocity time graph is the area under the graph. Okay. So if we can work out the area under the curve or under the graph, we need to work out so that the total distance is 75. Okay. So the graph has got two main areas. It's got this part from 0 to 4 seconds where the horse is clearly accelerating. So it's accelerating from not moving up to a speed of 10. Once it gets to 10, it's just carrying on at the same speed, isn't it? Okay, so that's quite handy. It means we can break our shape down into a triangle, this part here. So let's just divide it up into a triangle and a rectangle. Now I don't know where to draw the line of the rectangle. It's not necessarily at 12. I need to draw the other end of the rectangle at a point which will make the total area be 75. So we're going to have to kind of work backwards a little bit to find that. Okay, let's first off work the area for this triangle. So the area of a triangle is half base height, isn't it? Okay, so this is going to be a half times the base of this triangle is 4 times the height, which is 10. So that's 2 tens, that's 20. Okay, so that's got an area of 20. So it means the horse covered 20 meters while accelerating in that first 4 seconds. Okay, so what's left? It needs to run 75 altogether. So 75 subtract 20, that leaves me with 55. So this area of the rectangle needs to have an area of 55 so that the whole area is going to be 75. Okay, now the height of this rectangle is 10 because that's the height it's at. So 10 times something is 55. What is the something? It's going to be 5.5 then, isn't it? So 55 divided by 10 is 5.5. That means that the other line of my rectangle has to be 5.5 units beyond 4 then, isn't it? So it's going to take me up to 9.5. Okay, so that is 9.5. Okay, giving me an area of 55, a total distance travelled of 75, and that tells me then that the horse has covered 75 meters in 9.5 seconds. So after how many seconds has the horse run a distance of 75 meters? In 9.5 seconds. Okay. Okay, question 23 has a speed time graph for a car journey. So we've got time along the bottom and speed up the side, and we need to estimate the acceleration at 6 seconds. Now acceleration is the gradient of a speed time graph. So if we have a look at the graph at the point where t is equal to 6, so reading up from 6, we're talking about this point here on the graph. What is the gradient of the graph at that point? Now you notice it's a curved section of the graph, so it's not about taking 2 points on the line and working out the gradient. What we need to do is we need to take our ruler and draw on a tangent at that point. So we try and get the ruler to just touch the point so that the gaps between the ruler and the line either side are about the same, and then we can draw on our tangent at that point. Okay, and then we need to find the gradient of that line. Okay, so taking 2 points on this line, let's take this point here, that's the point 0, what's the scale here? Each one of those little squares is a fifth of 2 units, isn't it? That's not very helpful. So 5 divisions between 2 units means that each division is 0.4, so I would read that one as 3.2. So this point, coordinate down here is 0, 3.2. Let's pick another one further up. Let's pick this point up here at 10. So when x is 10, or t is 10, what's that then again? It's about 3 squares up, so 10, 11.2. Okay, so then we need to work out what the change in y and the change in x are between these 2 points. So let's draw on a triangle. So how far is it in the direction of y? Well, 11.2 subtract 3.2 is 8, and in the direction of x, 10 take away 0, easy peasy, it's 10. That's a bit why I picked those points. So now I know that, I can work out the gradient of the tangent. So gradient of tangent at x equals 6, gradient of tangent is equal to change in y, 11.2 minus 3.2 over 10 minus 0, which is 8 over 10, which is 0.8. So the acceleration then is 0.8 meters per second per second. So meters per second squared. Being very naughty here and writing over the lines. Don't do that in the exam. Part B wants us to estimate the average speed of the car for the journey. So we all know that average speed equals total distance travelled divided by time taken. Okay, so basically we need to know, we know the time taken, but the distance is what we're going to need to work out. Now you'll remember that the distance on a speed time graph is given as the area under the curve or under the graph. Okay, now this graph is made up of 3 distinct parts. I can divide it up into a triangle, a rectangle, and this rather more difficult shape here with a curved edge. This is the bit I'm going to have to estimate. I'm going to have to estimate the area of that section. Okay. Now, probably the easiest way, but most rough and ready way of estimating is saying, well, let's just assume, rather than having a curved thing like that, let's make it into a triangle and then work out those 3 areas. So working out this area, and the area of that triangle underneath there. Now obviously it's going to be a underestimation of the area because I've got that shape in the middle that I won't have calculated, but it's an estimate and I think it's going to be good enough for our purposes. So this area here is a triangle, so it's a half base height, isn't it? So that's going to be a half times 18 to 24 is 6 times a height of 12. So half 6 is 3, 3 6s are 36. This bit here is a rectangle, so just length times width. It's going to have an area of 14 to 18 is 4 times a height of 12. 4 12s are 48. And then this bit here is a triangle, so again half base times height, which is a half of 12 times 14. Half of 12 is 6. 6 14s, what's that, 84? Okay, so let's write that in our answer sheet. It's 84, 46, and what was it? 36, 48, and 84. 48, 84, and 36 over total time taken. Well, the time of the journey was 0 to 24, so it took 24 seconds over 24. So let's add that up. 84 plus 48 plus 36 is 168 divided by 24, and 168 divided by 24 is 7. So average speed is 7 meters per second. So 7. Okay, now the last part of the question says evaluate your answer to part B. Is it an underestimate, an exact value, or an overestimate? Well, as I said earlier, we have estimated this area under the curve section to be a triangle, so we've missed off this bit in here. Okay, so we have underestimated the distance that was travelled in the time taken. So if in our calculation the distance was low, then we've got a low number divided by a number, so this speed then is going to be a low. It's going to be an underestimate. So oops, it's going to be an underestimate. We need to write a comment with that, so so what did we do? We estimated area under curved section to a triangle which was less than the area under the curve. Okay. Question 23. Here is a velocity time graph of a motorbike for 25 seconds. After how many seconds was the acceleration 0? Okay, well, the acceleration is going to be the gradient of the velocity time graph, and the acceleration is 0 when the graph is flat. So you can see, where is it flat? It's going to be flat here at this point here, or more in particular right in the middle of there. So at that point there, look, it's flat. So reading down to the graph, reading down to the axes below, it's there, isn't it? Now that is, well, you can see I've got 10 divisions between 0 and 5, so each division must be a half, or 2 divisions, or 2 little squares is 1. So I make that 6 then. So after how many seconds was the acceleration 0? It's going to be after 6 seconds. And then it says work out the distance travelled in the last 15 seconds. Now, distance travelled is the area under a velocity time graph, and the last 15 seconds is So 25 seconds less 15 is 10. So it's this section here. Right. Sort my pen out. So from here down to here. Now you'll see that this section of the graph is a straight line. Can't seem to draw on there. Okay, that's it. So this section here we're looking for. Okay, so that's the section of the graph is a straight line. So the shape we've got is a trapezium. So the area of a trapezium is going to be the two parallel sides added together divided by 2 times the distance between them. So this is my A value here, isn't it? Which is of a height 22. So A is 22. This is my B line on the other side. That is at a height of, I make that 18. Distance between them is this distance. We said for the last 15 seconds. So it's that 15 there. So distance travelled is going to be a half A plus B times H, the formula for a trapezium, which was a half of 22 plus 18 times 15. Got those right? 22, 18, 15, yeah. So half of 22 plus 18. 22 plus 18 is 40 divided by 2. So half times 40 times 15. Half of 40 is 20. 20 15s are 300. So it's 300 meters. Question 24. The speed time graph shows 20 seconds of a car journey. Harry wants to estimate the distance the car travels in this time. He uses a triangle and a trapezium as shown to estimate the area under the graph. Okay, so we've got a speed time graph, and you should know that the area under a speed time graph is the distance travelled, and we need to complete Harry's method to estimate the distance the car travels. So basically we're going to find the area of these two shapes and use it as an approximation as the total area or the total distance travelled. Okay, so how do I find the area of a triangle? Area of a triangle is a half base times height. So my base here is this distance, which is 10, and my height is this distance, which is 20. So then my area is going to be a half times the base, which is 10, times the height, which is 20. So half 10 times 20, well, half of 20 is 10, and 10 times 10 is 100. So that's 100 meters. Okay, so that's the triangle. Now for a trapezium, area is equal to a half A plus B times H, where A and B are parallel sides. So basically you're averaging out your two parallel sides and you're multiplying by the distance between them. So I already know A, it's that 20. B is going to be this length here, isn't it? Which is 30. And then the distance between them is going to be my H value. Distance between 10 and 20 is 10. Okay, so my area here is going to be a half 20 plus 30 times by 10. 20 plus 30 is 50. Half of 50 is 25, and 25 times 10 is 250. Okay, so my total area under curve is going to be the area of the triangle plus the area of the trapezium, which is 100 plus 250, which is 350. And the units must be what we've got, meters per second and seconds. So that must come out to be meters then. 350 meters. Question 24b. For this journey, which of these is true for Harry's method? Tick one box. Okay, it works out as an overestimate of the distance. It works out as an underestimate of the distance. It could work out as an overestimate or an underestimate of the distance. Okay, well, let's have a look at the method. Go away, silly thing. All right, so I've got a triangle here which is pretty much spot on, but my trapezium, look, when I calculate the trapezium, I'm not calculating this bit up here. So the true area under the graph is a little bit bigger than the area that I've calculated. So what I've calculated, this 350, is going to be an underestimation because I haven't calculated that bit there and included it in my answer. So it's an underestimate of the distance. Question 24. Beth ran a 200-meter race. Here is a graph of the first 8 seconds of her race. She completed the race at a constant speed of 9 meters per second. Okay, so we've got a speed time graph here. And we're told underneath that Amy completed the race in 27 seconds. Did Beth finish before Amy? You must show your working. Okay, so we were told that Beth continues the race at 9 meters per second. So I can get a ruler out and draw the rest of her speed time graph. So it's just going to flatline after there. So the rest of the graph is going to be a flat line until she finishes. I'm not quite sure when she finishes. Maybe we should work that out. So she's got to cover 200 meters. Now we know that the area is the distance under the graph. So if I just draw a line there and work out the area that she covered in the first part of the course where she was accelerating. So that is a triangle. So the area under the graph is going to be a triangle of base 8 and height 9. So half base times height is going to be a half of 8 times 9. So 4 9s are 36. So she covered 36 meters in that first part of the graph where she was accelerating, which means that the other part of the graph, which is going to be a rectangle, has an area of 200 minus that 36 meters, which is 164. So it's going to have an area of 164. Now we already know that the height of the rectangle is going to have to be 9. So if I divide 164 by 9, I'll know the length of that rectangle. 164 divided by 9 is 18.2. So it's going to take her another 18.2 seconds to finish. So if she's at 8 seconds, then she's going to finish 18.2 seconds beyond that, which is at 26.2. So completing the graph unnecessarily because I've already got the answer, haven't I? But let's just finish it off for completion's sake. So 164 divided by 9 tells me that was 16.2. So she must have finished the race. So it was 18.2, wasn't it? So she must have finished the race at 26.2 seconds. So Beth finishes at 26.2 seconds. So did she beat Amy? Of course she did. She was 0.8 seconds quicker. So she does finish before Amy. Go Beth. Question 25. Here is a speed time graph for a 50-second journey. So we've got speed up the side there and time along the bottom. Circle the acceleration in meters per second halfway through the journey. Okay, what's halfway through the journey? What, 25 seconds in? So looking up from 25, we're talking about this point here in the journey, aren't we? Okay. So what is the acceleration there? Okay, well, acceleration on a speed time graph is given by the gradient, and the gradient here is pretty darn flat. Okay, so this is going to have a acceleration of 0 in this current section. It's not accelerating at all. The speed is constant. So acceleration is the rate of change of the speed, and the speed is not changing, so there is no acceleration, so the acceleration is 0. Okay, and I hope the next part is more interesting. Part B says work out the total distance traveled. Okay, so the distance traveled is area under a speed time graph, so we need to work out the area of this shape here. Now you can do it two ways. You can say that the area is made up of a rectangle and two triangles and work them all out and add them together, or the smarter way is just realizing it's a trapezium and using the trapezium formula, okay, which is a half a plus b h, okay, where a and b are your two parallel sides. So a is going to be this side, b is going to be this side, and then h is the distance between them, so it's that distance there. Okay, so what's that then? That's half of a, which is goes between 10 and 40, so it's going to be 30, plus b, which goes between 0 and 50, so that's 50, and h, which goes from 0 to 20, so that's 20. Okay, so I think I'm just going to go ahead straight away and halve the 20 and get 10. And then I'm going to add my 30 and the 50 and get 80, and then I'm going to do 80 times 10, that is 800. Okay, so 800, what do you call it? Well, if it's in meters per second and you're multiplying it by seconds, then you're going to get meters, aren't you? So that is 800 meters. So what is the total distance traveled? 800 meters. Question 26. Helena ran an 800-meter race in 140 seconds. The speed time graph represents the first 100 seconds of her run. Helena ran the last 40 seconds with a constant deceleration. Work out her speed as she finished the race. Okay. Now, I've seen quite a few students just assume that line, because it's a constant deceleration and it's the end of the race, they assume that it's going to go like that. So it's going to run down and hit to 140 at 0. But she's not going to be finishing the race at 0 meters per second. Otherwise, she'd never get there. You know, she really slowed off that far. She's never going to actually get there, is she? But we actually need to find the speed that she finishes the race. We can't just assume that she finishes at speed 0, just kind of slows right down and just kind of crosses the line at a snail's pace. That's not what happens. It's going to be more like this. So she's going to constantly decelerate, and we need to find the level at which the speed she's going to be at the point where she finishes the race. Okay. Now the way we can do that is the fact that we know that it was an 800-meter race. So we know the distance traveled, and we know that the distance traveled is the area under a speed time graph. Okay. Now we've got 2/3 of the speed time graph already drawn. It's kind of in 3 sections, isn't it? It's this section here where she had her initial acceleration from the start. So she was starting from standstill and kind of zoomed off. Okay, so we can work out the area of that little triangle bit. Then she's got that period of constant speed that she's running, which is a rectangle, so it should be fairly easy to work out that area. And then if I take that away from 800, then I should be able to work out the area of what is going to be a trapezium at the end, and then we can find out maybe the height of the trapezium after that. Okay, so what is the area of this section here then? So that one is area 1. So area 1 is a triangle, so half base height, which is the half of the base, which is 10, the distance from there to there, and a height of 6. So half times 10 times 6, that's 30. So 30 meters was traveled in that little triangle bit. Then the next section, this bit here then, it's going to be my area 2. That's a rectangle, so it has formula length times width. The length is the distance from 10, or the time from 10 to 100, so that's 90. And the height is just 6, isn't it? So 90 times 6. So what's 90 times 6? 90 times 6, that's 540 meters. Okay? So altogether, from section 1 and 2, she's done 540 plus 30. So the remainder, area 3, is going to be the 800 meters, the entire length, minus those two, isn't it? It's going to be minus 540 and 30. Okay, so we know then that the area of the trapezium is going to have to be 800 take away 570, which is 230, isn't it? Okay, so the area of the trapezium has to be 230. Now, we know some things about the trapezium, and we don't know one thing about the trapezium, which is the length of one of the sides, don't we? So if we think about what we know about the trapezium, we've got like one side which we know is like the equivalent of this side here, which is going to be a height of 6. We know the length, that distance there is actually the height of the trapezium, because there's a trapezium on its side. That's going to be 40. We don't know this is what we're trying to find. This is x, okay, and then it's going to come down like that. And we know that the area inside it has to be 230, okay? So given that the area of a trapezium is half a plus b h, where a and b is our two parallel sides, we know that that is equal to a half times, well, our unknown value x plus the 6 plus the distance between them, which is 40. Okay, so that comes out to be half of 40 is 20, so that's going to be 20x plus 6 lots of 20s plus 120. Okay, so, and we know that's equal to 230, so we can form an equation in x to solve then. So if 20x plus 120 is equal to 230, so taking 120 away from both sides, that means 20x equals 110. So then x is going to be 110 divided by 20. So 110 divided by 20, that's 5.5, isn't it? Okay, so x is 5.5. Okay, so she's going to be finishing the race at x equals 5.5 meters per second. Okay, so in order to finish off, if you wanted to finish this this trapezium off, then it's actually going to finish at that height then, isn't it? It's going to just be like she's just falling off a little bit in speed. You know, she's trying to win the race. She's just tiring a little bit, but she still wants to win. So, you know, she's not going to end at a crawl, is she? So it's going to end up looking like that with an area of 230 then, isn't it, in there? Okay, so yeah, 5.5 is the speed she finishes. Question 27. Here is a sketch of a speed-time graph for part of a journey. So we can see it's made up of 3 distinct areas. So the vehicle, or whatever it is starting from rest, is speeding up between 0 and the point A. Then it's traveling at a constant speed, and then it starts to slow slightly until it gets to the point C. Now, we are told in the question that the average speed from 0 to t seconds was 7.2 meters per second, and we want to work out the value of t. Okay, so from the average speed, we should be able to work out the total distance travelled in that amount of time. And we also know that the area under a speed-time graph is equal to the distance travelled, and this distance is made up of 3 very easily calculable shapes. We've got a triangle, we've got a rectangle, we've got a trapezium. So what we're going to do is we're going to work out what the areas of these 3 shapes are, and we're going to compare them to the average speed, well, the distance given by the average speed over that amount of time. Okay, so easy peasy. Let's give it a go. So using our DST triangle, so we know that average speed equals distance divided by time, so distance is speed times time. So the total distance travelled is going to be speed times time, which is 7.2 times the time taken which is t. So it's equal to 7.2t. So it's going to be an equation we're going to have to solve then, isn't it? Okay, and then coming back to the area then, but distance travelled is also area under graph, which in this case is going to be my area of my triangle plus my area of my rectangle plus my area of my trapezium. Okay, so area of my triangle is going to be half base times height, isn't it? So it's going to be half 8 times 9. My area of my rectangle is my, so that was 8, that was 9, wasn't it? Now the base of this, or the length of my rectangle, is going to be the difference between 8 and 14, which is 6. It's also got a height of 9, so that's going to be 6 times 9. And then my trapezium, to find the trapezium, you average out your two parallel sides, so it would be 9 plus 7 over 2 times the distance between them. Now that distance is going to be t subtract 14. Does that make sense? So it's going to be half of, I hate when I squish things up at one end, 9 plus 7 times t subtract 14. Okay, so half 8 times 9 is, half of 8 is 4, 4 times 9 is 36, 6 9s are 54, that was rather messy that I wrote down, but 9 plus 7 is 16, divided by 2 is 8, so that's 8 lots of t minus 14. And we know that that is the same thing as 7.2t. So you'll see we've got an equation in t, which we can now solve. So let's do that. So 7.2t is equal to, well, 36 and 54 adds up to 90. Then removing the brackets over here, I'm going to get 8t minus 8 lots of 14. What's that? 80 and 32, so 112. Now rearranging, so I've got all the t's on one side and all the numbers on the other. I think it would be easier to collect t's on the right, keep it positive, and then numbers go to the left then. So I'm going to get 112 minus 90 equals 8t minus 7.2t. So that's going to give me 0.8t on the right, and 112 take away 90 is 22. So 0.8t is 22. So then dividing by 0.8 should give me the value of t. So I make that t equals 27.5.
Question 28. Izzy runs an 80-meter race in 14 seconds. During her first 6 seconds, her speed increases at a constant rate. During her last 8 seconds, her speed increases at a different constant rate. Her speed at 14 seconds is 2 meters per second more than her speed at 6 seconds. Here is a sketch of her speed time graph. And question 28a says, work out her acceleration during the last 8 seconds. Okay. Now the last 8 seconds is, well, it's the time from 6 to 14, isn't it? That's 8 seconds long. So we're talking about this section of the curve, of the graph here. And acceleration is equivalent to the gradient on a speed time graph. So acceleration equals gradient at that point. Okay, now I don't know how fast she was going at time 6. Let's call it x. But I do know that at time 14 she was going 2 seconds more, 2 meters per second more than her speed at 6 seconds. So if this value was x, then this value is x plus 2, which means that distance between there and there must be 2. Okay, so I don't know what x is, but I know that that one up there is 2 more. So I do know the change in y. The change in x is just 14 minus 6. That's 8, isn't it? So the acceleration is going to be the change in y, 2, divided by the change in x, 8, which is the same thing as a quarter, or 0.25. State the units of your answer. Okay, well, we're using meters per second. So then the speed is going, so the acceleration is going to be 0.25 meters per second, or ms to the minus 2. Okay. Okay, what's part B say? When Izzy finishes the 80-meter race, her speed is v. Work out the value of v. Okay, so we actually need to then work out what this value up here is going to be. So this thing earlier I called x plus 2, that's going to be the v that I need to find then, isn't it? Okay, right, so how am I going to find that then? Well, the only other information on this question that I haven't used yet is this, the fact that Izzy runs an 80-meter race in 14 seconds. Now, I know that the area under a speed-time graph is equal to the distance travelled. So if I can find the area under the graph, that might give me some clues about how to find v. Okay, so breaking up my graph into 2 distinct areas, I've got a triangle down here and I've got a trapezium. Okay, now let's say that the speed at, we said was x, wasn't it? So the area of this first triangle then is half base times height. So this bit here is going to be a half base height, which is equal to a half times the baseline, which is 6, times a height, which we called x. So half times 6 times x. That means that this has an area of 3x, doesn't it? Okay, so the triangle is an area of 3x. What about the trapezium? Now a trapezium, oops, come back. A trapezium, it has a formula half a plus b h. Okay, so where a and b are the 2 parallel sides. Okay, so my first parallel side, this one, we already know is x, and my other parallel side, this one, we called x plus 2. X plus 2 times h is the distance between them, isn't it? So that distance there, which we know is 8. Okay, so what's the area of that then? Half 8 is 4. X plus 2 is 2x plus 2. Half 8 is 4 times 4. So just multiplying everything in the bracket by 4, I'm going to get 8x plus 8 then, isn't it? So that area is 8x plus 8. So the combined area then is 3x plus 8x plus 8. Okay? So, distance equals area under graph. So our 80 meters is equal to my 3x, my triangle, plus my 8x plus 8, my trapezium. So 80 then is equal to 11x plus 8. Okay, so what's that then? Taking 8 off both sides, 72 equals 11x, dividing through by 11. X then is going to be 72 over 11. Okay, so x is 72 over 11. Remember I wanted to find v though, which is x plus 2, so I need to add 2 to that. So v then, v is equal to should really do it down here, I suppose. So v is equal to my x plus 2. So I said it was 72 over 11 plus 2 then. So what is 72 over 11 plus 2? 72 over 11 plus 2, that's 94 over 11. What's that then? 8.54 reoccurring. So 8.5454, I'm just going to round that off then to 8.55 meters per second then, isn't it? Because it's velocity. 8.55. Question 28. Leo runs for 12 seconds. The graph shows his speed. So up the side we've got speed in meters per second, and along the bottom we've got time. So this is a speed time graph. Show that the distance he runs is less than 67.5 meters. Now, distance traveled is the same thing as the area under a speed time graph. So we need to find this area here. Now, it's made up of a complex shape, but it's made up of some easier shapes. If I get my ruler out, I can take this odd shape and I can divide it up into a triangle and a trapezium. What about this last shape here? It's got a curved edge. I'm going to estimate this last bit. I think that's why it's asking me to say that it's less than something. I'm going to draw a line from there to there, and I'm going to say that this last section is a little bit less than this triangle here. Okay, so I've got 3 parts. I've got this part, 1, 2, and 3. Okay, I need to find the area of these 3 shapes and then add it together, and then that will be my estimate for the distance traveled. So area 1, now that's a triangle, so it's half base times height, isn't it? So the baseline runs from 0 to 5, so a half of 5, and then the height goes from 0 up to 8, so half times 5 times 8. Half of 8 is 4, 5 fours is 20, so that has an area of 20. Second section, area 2. Now that is a trapezium. So the formula for the area of a trapezium is half a plus b times h, where a and b are the 2 parallel sides and h is the distance between them. So my a value then is from here to here, isn't it? It's got so a is 8, b is 9, and then the distance between them is 4 then, isn't it? Okay, so that's going to be half of 8 plus 9 times 4. That comes out to be half of 4 is 2, 8 plus 9 is 17 times 2 is 34. And then finally I've got area 3. Now area 3 is going to be slightly less than the triangle I've drawn, isn't it? Which has got a height of 9 and a base of 3. So we can say that area 3 is going to be less than half base height, which is half times 9 times 3. So 9 threes are 9, 18, 27 divided by 2 is what, 13.5. So area 3 is just slightly less than 13.5. Okay, so then the combined area is going to be slightly less than, of those 3 things added together, 20 plus 34 plus 13.5, which is, just double check, I think it should be what they asked us it to be, so 67.5. Okay, which is what we were asking for, wasn't it? Yeah, less than 67.5, so we're done. Well, I hope this video helped you get a better overview of the topic. If it did, give it a thumbs up. You can find more exam question compilations over here. For more past paper walkthroughs, click down here. If you want to visit my Amazon shop with my recommendations for calculators, revision guides and other maths related stuff, click down here. Good luck in your revision and in your exams, and see you again.